Okay, this is Physics 1A for Monday, March 8th. Today we're going to be moving on from equilibrium and start talking about things that move. Everything up till now has just been basically either at rest or moving with a constant velocity. So we're going to introduce the concepts of displacement, average velocity, instantaneous velocity, speed, acceleration. We'll derive a lot of equations you've probably seen before, like the kinematics equations, and then we'll solve some problems, or I'll probably have you all solve some problems. Okay, so before I get started, does everything look okay on the stream? I guess I had to redo some things with it today, so some of the stuff may have been altered somehow. Does everything look okay? Looks good? Okay. Alright, so get back to where I can read it. Yeah, so we need to start off with talking about displacement and how it's different from just distance. So let's get going with that. So the first thing we need to do is we need to kind of define some terms. And the first term that we're going to define is the position of an object. So the word position, here, let's erase that. It's kind of weird. In physics, or in just mathematics, is going to refer to kind of the location of an object relative to a fixed point. So I'll write all that out. Okay, position. This is usually represented by like an x, y, or z coordinate of an object, and the position may be described with up to 3 variables, x, y, and z for like the location. In this particular section of the class, we're going to start off by just talking about one-dimensional motion, which means all of our position is going to be defined with just the letter x, basically. So we'll use the symbol x to represent the position of an object, and the symbol x is just going to represent the distance from some origin. Okay, so for example, if you had, let's say this is the ground, and let's say you have some kind of a house right here, and let's say you want to define the location of some car or something like that. So you've got a car right here that's just left the house or something like that. Then you pick a point, like maybe this point right here, and you define that point to be x equal to 0. That's going to be your fixed point. That's what we call x equal to 0. And then you could define the location of this car right here to just be some, maybe you talk about the back side of the car, maybe you talk about the front side of the car. You've got to pick a point, and you call that distance right there x, right? And maybe in this case, that distance is like, let's say 5 meters or something like that. And that's just going to be the straight line distance. I didn't make it super straight here, but if we put a line in here, it's going to be the straight line distance between these 2 points right here. Shift that a little bit. Okay, that's a pretty obvious definition, right? There's nothing special about that. Okay, so it's like the x coordinate of an object relative to some point. You pick whatever fixed point you want. That's going to then define what your x coordinates are. Okay, so once we've defined that, then we could talk about what happens if this car, for example, were to move between 2 locations, okay? And for that, we need to define something that's called displacement. So displacement can be thought of as being like the change in position of an object when it moves from one location to another, okay? So we're going to define this as a vector, and I might not always put a vector symbol over this, but I'll try to when it makes sense. So delta x, like this, is going to be a vector. The delta means the change in x, and this is going to be equal to basically just whatever the change in coordinates for the object is. So if an object moves from one position that we call x1 to another position that we call x2, then the displacement will just be x2 minus x1, all right? So in the case of this car up here, we could say, suppose the car starts right here at position x1, and then the whole car moves to a new location. Let's see if I can just copy and paste the car. If it moves to a new location, let's say right here, and maybe that new location has an x-coordinate x2 that we call, I don't know, 7 meters, then the displacement would be a vector. I'll use a different color. I'll use the actual vector symbol. And let's draw it above here, because I don't want to. The displacement would be a vector that would go from here to here, like that. And that vector would be what we would call delta x. Ooh, that is a really thick marker right there. I'm going to have to, this is going to be kind of frustrating today. I'm going to have to go through and kind of reset all of these things. So that's going to be delta x right there. Look, that's just too hard to read, I think. Write it again. Delta x. and it would be equal to x2 minus x1, and it would be equal to 7 minus 5, which is going to be positive 2 meters. And I'll go ahead and put another vector symbol up here. Now, the direction of this displacement, in the case of, since we're just talking about one-dimensional motion, is entirely going to be given by that symbol right there. So that's the direction. In this case, the direction is to the right, which we're defining as positive. Okay? And that's what displacement is. You take the final position minus the initial position, and it gives you a vector describing kind of where it started from and where it ended up. That's what displacement is. Do I need to write any words down for that, or is that pretty clear what I mean by that? All right. So the thing to distinguish this from would be the word distance, because they're not the same thing. So distance is just how far something travels, basically. You know, 1 second. Oops. Okay, so let me give you an example of this and how it's different. In 2 dimensions, this is really easy to describe. So maybe we'll describe it in 1 dimension first, and then I'll describe it in 2 dimensions. So let's take an object. Here, let's use some actual straight lines too. You got a straight line, and on this straight line we have, let's just draw a person. That's easy enough to draw, right? Okay, so let's say that this person starts off right here, and I can already see that it's way too thick. So let's say that this point right here is defined to be x equal to 0, right? And this is going to be the starting coordinate of my person, and let's say x1 is equal to, we'll just pick 2 meters for this point. Let's say that this person moves from this location to here, and let's say that the location that they move to here we call x2, and say that it's equal to like 7 meters maybe. And then let's say that this person, what they do is they walk in a line this way, right? They get to this location, so they walk straight that way. But then when they get there, let's say that they turn around and they go back to here. Okay, so they basically travel along a path like this, right? Still in a straight line. So the person walks from this position to this position, and then they move back to a position like right here. Where, let's call this one 2, 7. This looks like it's probably like, what, like 5 or something? And we'll call that one x3 and say that it's equal to 5 meters. Alright, so let's talk about the displacement between the beginning point and the ending point. Can anyone tell me what that would be equal to? What is the displacement to go from from x1 over to x3? It's 3 meters. Is it positive or negative? It's positive, right? Because you would do 5 meters minus 2 meters, and you would get a positive 3 meters, right? Okay, so for distance, we're going to use this. So let's write down here on the left what these are all called. So displacement is delta x. And again, you can put a vector on this if you want to. It's kind of weird in 1 dimension, but you definitely can do it. Then distance is, we're going to use the symbol just d for distance. So the next question would be, how far did this person actually travel going from x1 to x3? What's that equal to? So they went from 2 to 7, which is 5 meters, right? So the total distance traveled, d. Looks like everybody's saying 7. I think that's right, because you would go from 2 to 5, or 2 to 7, which is 5 meters. And then you also have to include the distance the person traveled backwards, which is 2 meters. So you'd add 2 meters to that. And that equals 7. Now these numbers just happen to work out like this. It's yeah, it's kind of weird that this is 5 minus 2 and 5 plus 2. It's not always going to work out like this, but in this case it happened to work out like that. So you can see the distance traveled is 7 meters, which is farther. That's not surprising because the person walked forward and then walked backward. But the displacement only indicates from where the person started to where the person ended. It doesn't matter if you turn around at all. It's not important when it comes to displacement, if that makes any sense. All right. So if we've defined those, and nobody has any questions about that. Does anyone have any questions? Then what we can do next is we can define things like speed and velocity, okay? So we'll start off by defining speed. So speed is going to be the distance something travels divided by the time interval, which I'll write down as delta t, okay? So it's basically just total distance traveled divided by the time that it takes to travel that distance. So there's just the time taken, delta t. All right. Symbol for speed, I don't know. There's not really like a generally accepted symbol for speed. I guess you could use S if you want to. But when we do this calculation like this, this represents what we call average speed. Okay? Your average speed. If you think about this, what this means is, imagine you're driving along a straight road, and you start from 0 miles an hour. You speed up to 20. You travel for a while, and then you slow down to 10. You speed up to 50. You change your speed as you move, right? As we all do as we're driving along the road, right? If you think about just your average commute between your house and, let's say, a store or something like that, you don't go a constant speed the entire way, right? You tend to speed up and slow down. You have to stop at stop signs, stop lights. You have to make turns. And so your average speed doesn't care about how many turns you take, how many stops you take, or anything like that. Those just add up into the total time. And to find the average speed, you just look at the total distance traveled and divide by the time taken, right? So if you're driving across the road, and let's say you drive 500 miles, and it takes 10 hours, right? So if you drive 500 miles, like you're driving on a road trip, and you look at your odometer and you see how far you're traveling, it says 500 miles. And if it took you, let's say, 10 hours to do that, then your average speed would be 50 miles an hour. Okay? Pretty simple. This number will always be positive, because speed is a scalar, and it does not have a direction associated with it. Okay? So this is a scalar quantity, which means it will always be positive. Well, scalars don't always have to be positive, I should say, but average speed will always be positive. All right. So that's our definition for average speed. I don't know if I'm going to use a symbol for this or not, but we'll see. Sometimes I'll use just V average or something, but yeah. The next thing to define then is just average velocity. So velocity is a measurement of not only how fast you're going, but it also includes the direction that you move. So for this one, we need to have some kind of a vector associated with it. The symbol that we can use for this one is going to be V average, with the vector symbol over it like this. Your book also likes to write V average X down here like this. And I think things get a little confusing if we write that all the time, so I'm going to leave that off for now. I may put it back in later in certain times. So V average, then, is just going to be your displacement, delta x, divided by delta t. And by not putting an x right here, we can say that even though we're only talking about one dimension, average velocity will always just be displacement divided by time, no matter how many dimensions you use, okay? It's always going to be displacement divided by time like that. So this is a vector, and it might be something like, you know, instead of just being 50 miles an hour like a scalar like this, it might be that you drove 50 miles an hour. You may have driven 500 miles to the east or something like this, so it would be 50 miles an hour east, for example. You have to include the direction for the average velocity, right? Okay. Any questions about that? So let's look at a kind of, not really an example. We're just going to use a couple pictures from the textbook to do some things here. kind of want to draw our own graph, but maybe we'll just use their graph. Okay, so we've got a car right here. And we've got a table. I'll put the table right here. Maybe I'll go up higher so we can see all the definitions too. So here's our car. The car moves between, 6 locations. So you have like a number line, basically. And that number line has a 0 right in the middle. That's x equal to 0. All the distances are measured in meters along this number line. And we have a car that starts off right here at point A. It moves from A to B. And then from B, it turns around in reverse and goes to C. And from C, it goes to D, it goes to E, and it goes to F. And we know from this table right here where the car is at each of those times, at each of those locations, like the X location. And we're also given the time at which it's at that point. So at t equal to 0, it's at 30 meters. So you can see that the distance is not being measured by the left edge of the car, it's being measured by the middle of the car, which is fine. You just pick a point. And then it's a little past 50 here, which they're saying is 52. And then the car goes backwards to, 38, and then back to 0, negative 37, negative 53. So that's the motion that the car undergoes. It kind of does something similar to what this person up here does, where the car basically starts off right here, it goes to the right, and then it loops around, and it turns back around and goes back to here. Right? It kind of goes along a path kind of like that. That's what the car's doing. So what I want to do is I want to calculate the average velocity for this car and the average speed for this car at various different times, basically, right? So these are the things I want to calculate. I'll probably just have you all calculate them and tell me what you get as your answers. So, what do we want to do? We want to do displacement calculations? No. Let's do speed calculations. So what we want to do first is we want to find from A to B, we want to calculate the average speed and we also want to calculate the average velocity. And we're going to do the same thing from B to F. Probably leave a little bit of room. And then we're going to do the same thing from A to F for the whole trip, basically. We want to calculate the average speed and the average velocity. Let's just make a little table right here. Let's shift these down just a little bit. So we want to find average speed and average velocity for each of these different time intervals here. Make a little grid here. Could you all kind of take a minute or two to try to do that? Basically kind of fill out this table right here. Oops, copy paste. For these intervals, I want you to find the average speed and the average velocity. Given this data right here. Can you read this data okay? Do I need to make it bigger? Make it a little bigger. I'll give you like 2 minutes. That should be enough time to do all those calculations, right? And in case I didn't actually define this one, did I? So delta t means you just take the final time minus the initial time. So going, for example, from point A to point E, delta t would be 40 minus 0. From point C to point E, it'd be 40 minus 20, right? So 20 seconds. Okay, that was about 2 minutes. Let's go down the, we'll go left to right here. So, for this first box right here, we're going from A to B. What's the distance traveled? Don't look at the graph, you gotta look at these numbers right here. It's 22, right? Because it goes from 30 to 52, yeah. So it's 22 meters in the numerator. The time interval goes from 0 to 10, right? So we would do 10 seconds minus 0 seconds in the denominator. And so what do we get? 22 over 10, so 2.2, right? Okay. So what's different about the average velocity right here? Well, it's going to be probably the same answer, right? So this will be in the numerator. You'd have 52 minus 0, sorry, minus 30. And the denominator, you would have same thing, 10 seconds minus 0. And so we would get 2.2, but it would be positive, right? Positive 2.2 meters per second. So I'm just going to indicate that this is a velocity by saying that there's a positive number right here. So that's going to be your average velocity between those points. All right, from B to F. So going from point B down to point F right here. What's the total distance traveled? -52 minus -53, right? Basically, what you could do for this is you could just take the absolute value of this, and you could add it to this, right? Because it goes 52 meters forwards, and then it goes from... Sorry, that's not exactly right, is it? That's my bad. Here. This is not as simple to just write this one out, sorry. It goes 22 meters forward, right? So the forward motion, it goes 22. That's from... Oh, wait, B to F. I'm sorry. I'm being stupid. I'm not even looking at what I'm asking. Sorry. Okay. So it starts at point 52. It goes backwards 52, right? So 52 meters back. That's to 0. And then it goes another 53 meters back to point F. Oh, I apologize. That was extremely confusing. But 105 is right, what Chris said in the chat. For the total time from B to F, it's 50 minus 10. So that is equal to... What is that equal to if you do 105 over 40? $2.625? Okay. Okay, so maybe some of you have already calculated this, but what's the answer for the next part? Do you get the same answer? Same thing with the negative sign, that's right. Okay, for this one, this is actually maybe even easier to calculate, because delta x tells us to take the final position. The final position is that number right there, -53. Let me get rid of these absolute value signs. That's the final position, so you write -53 minus the initial position, which in this case, since we're going from B to F, is going to be +52. And then divide by 50 minus 10. So this one ends up being negative. That's our average velocity. Okay, so it feels like there's a pattern now, right? Like it feels like the average velocity and the speed, they seem to be the same, but the velocity has a positive or negative sign in front of it. That's what it seems like is the case. Yeah, Robert, in this chapter, I'm just going to use the negative and positive signs to indicate direction, okay? But absolutely, like, if you wanted to call this direction east, and you wanted to call this direction west, that'd be totally fine, too. Nothing wrong with that. All right, from A to F now. Now, to get the total distance traveled from A to F, it should probably be 22 plus 105, right? Because you go 22 meters forward that we saw from A to B, and then from B to F, yeah, okay, so 22 plus 105 would be, well, we'll write it out. So 22 meters forwards, and then 105 meters backwards, and we divide that by the total time, which is 50 minus 0. And now we're going to get whatever 127 over 50 is. 2.54. I'll write this one down here. Okay. Now for delta x, do you get the same answer? Sorry, for average velocity, are we going to get the same answer? You don't get the same answer. That's right. Because now, we don't care that it moved forward and backwards at all. All we care about is the final position, which is negative 53, minus the initial position, which was positive 30. And we divide that by the total time. So this is 83 over 50. Negative 1.66. Okay. So we've kind of broken the pattern now, where in the first two steps, the average velocity and the speed were exactly the same. The only difference was that the average velocity had a positive or negative sign in front of it. And one really common, I guess, mistake that students will make when they're distinguishing between velocity and speed is they'll think that speed is just the absolute value of velocity, and that's just not true. It's true as long as the car doesn't turn around, though, right? That speed and velocity will be the same number. But the moment that the car turns around, things change, because now the distance is growing, but the displacement isn't. So anyway, there we go. If displacement...
Mr. Murdoch?
Yeah.
I'm kind of confused on how you got the distance for A to F.
A to F?
Yeah.
Oh,
Like how'd
so
you get 105?
from A to B, we said it went 22 meters. And then from B to F, we found that it went 105 meters, because 52 plus 53.
Yeah.
And so then 22 plus 105.
I'm confused how you got 22, though.
What?
How'd you get 22 and the 105? I don't get... Where'd you get those distances from?
Okay, from A to B, the car went from point A, which is 30, to point B, which is 52, right? So the total distance the car moved from A to B, what's that equal to?
22.
So that's where that came from, right?
Yeah, okay.
And then, yeah, Robert, it's A to B to F.
Okay, I got it now.
What if we didn't have A to B? What do you mean, Andrew? I mean, we do in this case, so I don't. You mean if we hadn't done this part and this part, and we had to do the last part? Yeah, so we would just say, to find the total distance, we'd say, how far does it go forwards? So how far does it go from here to here? That would be one distance. Maybe you call it D1 or something like that. And then you have to calculate how far does it go backwards, which would be from here back to here. You'd call that one maybe D2 or something like that. And then you just add them together. Yeah, it's going forwards and backwards, exactly. That's okay. It's a static drawing. You can be forgiven for not being able to understand what's happening here. If we were in class, I would like take an object and I'd actually move it. But anyway. So in the body graph, D should equal 7 plus 5. 7 plus 2. No ton, because it started at x equal to 2. So it went forwards 5, and then backwards. So this would be like D1. And this would be like D2. Unless I'm crazy, it's 5 plus 2, right? Okay. So there we've got average speed and average velocity defined. And hopefully you can see that there's a little bit of a difference between them. Most of the calculations we do in this class will be with velocities. But that doesn't mean that speeds won't come up from time to time. And you'll definitely have problems where in your homework it may ask you to calculate speed or it may ask you to calculate velocity. Keep in mind that if the word velocity is used, right, velocity implies that you need not only the speed, but also the direction, right? You need the scalar portion and the vector part. Okay, so the next place to go from this... Oh, I guess we can look at this picture just to show something real quick. So we can also plot what this car is doing. The average speed formula is the same in 3 dimensions, and so is the average velocity formula, Andrew. They don't change. It's always going to be, speed will always be the total distance traveled, whether you go along a curvy road. So here's the 2-dimensional version of this. The 2-dimensional version, I think, maybe, in some ways, is a lot more intuitive. Suppose that you're traveling along a road that looks like this, as most roads do, right? Well, I don't know if most roads. As soon as you leave a city, right? Most roads are not straight. Most highways are straight, I guess. Suppose you travel along a road that's like this, right? So let's say you start off in your car, and your car is here, and I'm not going to try to draw a car on this, and it moves to here. So you start off here at point 1, and you move here to point 2. Okay, right? That's time 1 and time 2, right? If I want to describe the distance traveled along this road, assuming the car stays on the road, the distance traveled is going to follow the road, right? That would be the distance. Just however long that is, right? But for the displacement, you only care about the starting and ending point. So the displacement would go from point... Really? Shape. Click. There you go. Hopefully you're happy now. That's going to be displacement now. And I'm going to use this symbol for displacement in the future. So in 2 dimensions, it looks like this, where d is like the path length, and displacement is just a straight line drawn between the starting point and ending point. Okay? So does that make sense, Andrew? Okay, so now let's just look at this right here for just a moment and talk about this. Normally, we would just plot this in class, but it's going to be relatively time-consuming on OneNote to plot this, so I'm not going to do it. So what we have here is a plot. On the normal y-axis, we have x's, and on the normal x-axis, we have time. So time goes to the right, increasing. You can see that this is t equal to 0, t equal to 10, 20, 30, 40, 50 seconds. And this is the 0 point. This is x equal to 0 right here. And then x equal to 20 meters, 40 meters, 60 meters. So since our car starts at a position of 30 meters, it starts at x equal to 30, which is here, right? That distance is 30, right? And at that time, it's at point 0, right? And then we go through and we put all the rest of the points in. So B has an x-coordinate of 52. That looks like it's about 52 right there. It has a t-coordinate of 10. And you go in and you put all of the rest of your points in. And then we've drawn a smooth curve in brown that goes between each of the points to probably represent what the car is doing as it moves along these points. Now, on such a graph, what we can do is if we connect 2 points, like point A to point B, like this right here, then that line, that blue line right there, is going to have a slope. And if you calculate the slope, then you're going to get change in x over change in t, which is going to tell you the displacement, basically, right? So on a graph like this, that represents x as a function of t, or if you prefer to write it as x versus t, however you prefer to write it, then the slope of a secant line is the average velocity vector. Okay, so if we were to, for example, come here and draw a line to represent A to F from here to there. So that's what I mean by secant line, by the way. I don't know if you guys know this. A tangent line is a line that touches a curve just at one point, like that. A secant line is a line that touches a curve at 2 points, like a line like that. That would be the secant line between A and C, A and D. It's just a line. So if we drew a line between A and F right here, like that, then what I'm saying is that the slope of that red line right there should be the same as what we got right here, negative 1.66. And you can see why that would be, because you would take delta x, which would go from, this is the final and this is the initial. So you'd go xf minus xa, which would be negative 53 minus 30, just like we did up here. That's like the rise. And then you divide by the run, which goes from 0 to 50 here, right? And if you like, you can make a little box to say that, this is your delta t. Straighten up a little bit. And this is your delta x right here, right? So if we do the slope of the secant line, we're going to get velocity, right? This is delta x right here, and this is delta t over here. That makes sense? Now that shouldn't be too surprising, because I suspect probably in your math classes you probably did problems where there were objects that were moving, maybe in your physics 2A class, and you learned that if you plot something like distance versus time, if you take the slope is going to represent the rate of change of your curve, and that rate of change in physics we define as average velocity, basically. Just the rate at which the x-coordinate is changing. Anyone have any questions about that? So I think... Okay, Andrew has maybe a question. I'll let you write your question, and I will go grab what we're going to do next. I think is this. Oh, well, we got to talk about instantaneous velocity first, and then we will do that one. So there's two secant lines that are drawn on this graph. There's the line that I drew from A to F, and then there's a line that's drawn right here from A to B. But you understand that we could draw as many secant lines as we want to, right? I mean, I can draw one that goes from here to here. Oh, it just happens to be the case that the line that I drew from A to F also actually goes from E to F, which actually means that if we were to calculate... I wonder if this is true. We should calculate it. It looks, yeah, it actually looks like it goes straight through E, right? What does that mean? That means that if this line actually truly goes through E, then the average velocity between these points should be the same as the average velocity between A and F, right? Does everyone understand what I'm saying? It should be true. Let's see if it's true. Okay, this is something I haven't noticed before. I've done this particular example a lot. So if we went from E to F... Oh, way too big again. Oops. Down one size. If we go from E to F, then our delta x over delta t will be... So final position is negative 53 minus negative 37. That probably won't come out exactly the same, but I bet it's close. And then we divide by 50 minus 40. So this calculation should be really easy to do because we're just dividing by 10. As long as we can figure out how to add those numbers together. So this is an actual subtraction, right? This is going to be 37 minus 53. So that's, is it 16? It's got to be 16, right? So this ends up being equal to 1.6. Oh, it's negative 16, sorry. Meters per second. So if you compare that to this, it is pretty close. It's pretty close. These dots are kind of fat, right? Kind of fat dots. So it's like, you know, how exactly did I actually get it right on the A dot? How accurate is the picture they drew? But yeah, that's a good point, Andrew. It does work out that this is pretty much the same because the slope's the same. So it's a great point. Okay, so the next thing to do after having defined average velocity and speed is to define instantaneous velocity, something else we might be interested in. So to do that, we will use some things you learned in your calculus class, probably. So for instantaneous velocity, what we need to do is we need to find the velocity exactly at a point on our graph. 100% right at a point, okay? And the way that we can do that is we can talk about it graphically, or I can write down an equation. I'll start off with an equation, and then I'll show you what I mean graphically. So if I take the limit as the time interval between my points goes to 0 of the average velocity, which was delta x divided by delta t. then this will give me what we call instantaneous velocity. So we drop the average, and then this is our definition of what instantaneous velocity is, like this right here. The limit as delta t approaches 0 of delta x over delta t, that's our definition of what instantaneous velocity is. Now what that means on our graph up here would be, we're going to do a problem where we do this in a second here. What's a good 2 points to pick? We're going to pick points A and C because they are, maybe not. Let's pick points B and C. Or B and D, better probably. So if I draw that line on there right there, right? That line is going to represent the average velocity between points B and D, right? And this tells me to take the limit as delta t approaches 0, okay? So what that means is what I'll do is basically start making the time interval between my two endpoints get closer and closer to 0. So if I put them between B and D, what's the time interval between B and D? How much time goes from B to D? 20 seconds, right? So then if I cut that in half and instead go from B to C, the time interval is now 10. I can cut it in half again, and the time interval would drop to 5. And I could continue this process over and over and over again until the line that I draw becomes super tiny, basically, right? And if you go to the absolute extreme, what you're going to get is that this so-called secant line is going to become a tangent line, basically. Like this right here. So the other thing you can use for instantaneous velocity is you can just say that it's the slope of the tangent line at the point. And this thing, the slope of the tangent line to a curve, what would this slope up here be? I picked B because it feels like it's pretty easy to see. It's 0, right? Yeah. Does that make sense? Well, sure it does, because if we think about what was happening, this is saying that the velocity at point B is 0. And that almost has to be true, because with the way we set up our picture, right, the car started here, it moved to here, and at that moment it turned around and it started moving backwards, right? So if anytime something turns around, for a moment, its speed must drop to 0, right? Its velocity has to drop to 0 at that moment, right? Because it turned around. Because it went from going positive direction to negative direction. Positive velocity, negative velocity. And the only way to go from positive to negative is to cross through 0. There you go, that's right, Chris. We can also define this, since the slope of a tangent line, you take this whole course in calculus, calculus 1, where the whole point of the course is teaching you that to find the slope of a tangent line, you don't have to do this operation called the limit. That's what you do at the beginning of the course, right? But you can also just say that that same equation, here, let's get rid of this box for a second, that same equation is also found by doing the derivative. So that's the other way that we're going to define this. So the velocity can also be written as the rate of change of the position, or the derivative. Now this is where I'm going to go ahead and write down here that this is going to give you the x-coordinate of the velocity. Okay? Because what we'll learn in the next chapter is if I have something that's moving in the x, y, and z directions, if I want to find the z-coordinate of the velocity, I would take dz dt. If I wanted to find the y-coordinate, I do dy dt. But this is one-dimensional, so in this section it's just going to be dx dt here. Okay? Now this equation kind of looks a little bit weird, because you have a vector here with vx, you got a vector here with delta x. There's no longer really a vector for the derivative over here, right? So you're going to have to just say that when you take the derivative, if it's a positive number, it's pointing to the right. If it's a negative number, it's pointing to the left. So there we go. That's our definition of instantaneous velocity. And we're going to use this to solve a problem. It's 249. So let's kind of read this problem and set it up. Maybe we can do this in 10 minutes. It's not super hard, but it's kind of long. So it says a cheetah is crouched 20 meters to the east of a vehicle. So here's your vehicle. Here's your cheetah. Starts 20 meters away, right? The cheetah begins to run due east towards an antelope. So here's our antelope. That is 50 meters to the east of the vehicle. During the first 2 seconds of the chase, the cheetah's x-coordinate varies with time according to the equation x equal to 20 meters plus 5 meters per second squared t squared. We want to find the cheetah's displacement between t1 and t2 from 1 second to 2 seconds. We want to find its average velocity during that interval. And then we're going to find its instantaneous velocity by taking delta t equal to 0.1 seconds, 0.01 seconds, 0.001 seconds, and then finally we'll do the same thing by using the derivative. Okay, so again, we've got a cheetah right here. It's moving to the right. There's an antelope at this point 50, and the cheetah's x-coordinate as a function of time is given by that expression, 20 meters plus 5 meters per second squared times t squared. That's the equation we're going to be using throughout the problem. Okay, part A. Find the cheetah's displacement between t1 equal to 1 second and t2 equal to 2 seconds. So we're looking for displacement, right? And since we're going from 1 second to 2 seconds, what we're going to need is the x-coordinate at 2 seconds minus the x-coordinate at 1 second. When I write that expression right there, understand that I'm not saying x times 2 seconds. I'm saying the x-coordinate at a time equal to 2 seconds. So that means you basically plug 2 seconds into your equation here for t as a function, basically. Is that notation clear to everyone, or does that look weird to people? Is this a notation you're used to from your math classes?
Yeah.
Yeah. Okay. So let's do this calculation. All right. So delta x should be equal to x at 2 seconds is going to be So we just plug those two values in, and instead of calculating the whole thing, we'll individually calculate what each of these numbers are, because I'm pretty sure we're going to want to know what they are later on. So the first term is, what, 5 times 4 is 20, plus 20 is 40 meters. That's x at 2 seconds. I'm going to write that down here, because I feel like we're going to need it at some point. Did I get that right? 5 times 4? I think that's right. And then minus, this one's going to be 20 plus 5, which is 5. So we know x of 1 is 25 meters. And we just subtract them, because that's the definition of what displacement is, right? So we end up getting the delta x from 1 second to 2 seconds is 40 minus 25, which is 15. And it's positive, so I'll put a positive on there to indicate it goes to the right. That's part A. Any questions? So let's do part B then. For part B, now we want to find, this is where part B starts, find its average velocity during that interval. We just said average velocity is defined as delta x over delta t. So we take delta x, which was 40 minus 25. And we divide by delta t, which was 2 minus 2 seconds minus 1 second, and we get 50 meters per second. And that is our average velocity. Right there. The next thing we want to do is, this is the part where this gets to be a bit of a calculation. The next thing we want to do for part C is to find its instantaneous velocity at t1 equal to 1 second. So we want to find the instantaneous velocity here by taking delta t equal to 0.1 seconds, and then 0.01 seconds, and then 0.001 seconds. So I'm going to scroll down a little bit to make some room, because this part is going to have a lot of calculations. So there's 3 things to calculate here. The first thing is to calculate from t1 equal to 1 second up to, it says we want to take delta t equal to 0.1 seconds. What would t2 be then? If I say t1 is 1, I'm going to use a delta t, a change in time, of 0.1 seconds, then what would we use for t2? Is it a bad idea if I call it t2 here, because it's already called t2 here? Maybe. Maybe we call these like t initial and t final, so that there's no confusion about what we're doing here. What would t final be? 1.1, that's right. Since there seems to be some confusion, let's go back and read this kind of carefully here. I'm sure we're getting to the end of the hour here. I'm sure people are struggling to follow along, but it says find its velocity at t1 by taking delta t equal to 0.1. So this would be a delta t of 0.1, right? 1.1 minus 1. And now we want to find average velocity. So we have to do now the x-coordinate at the final moment, which is 1.1 seconds, minus the x-coordinate at the initial moment, which is 1.0 seconds. So do you see how this part differs from what we did this part right here? We're just reduced. So the first time interval was 1 second, right? And now the time interval is 0.1 seconds, basically. Do you all understand? Are there any questions I can answer to clarify what's going on here? That's right, Kelvin. Next thing we'll do will be from 1 second to 1.01 seconds. Maybe it makes more sense if I write that down below this. So the next thing that we'll calculate will be at an initial time equal to 1 second, and we're going to go up to a final time of 1.01 seconds. Because it says we want to do delta t equal to 0.1, delta t equal to 0.01, and delta t equal to 0.001. Really what we're doing is we're doing kind of a numerical limit, if you think about it. Because remember that we're doing delta x over delta t, and to find instantaneous velocity, we said you take the limit of this as delta t goes to 0. So we're just making delta t smaller and smaller and smaller. So let's go through the calculation. We'll see at the end if you understand what had happened here, Andrew. So this is the calculation. We need x of 1.1 seconds minus x of 1 second. Right? So that's going to be I don't know if I need to keep writing the second term here, but I guess I can. So our average velocity between these points. So the first one is going to be, can you calculate this for me real quick? Oh, I didn't charge my other phone. So my calculator's this one. It's 1.05. 1.05. You mean the total answer? Even that doesn't sound right. Oh. I'm being so bad. I'm so sorry. This is delta x. Right? This is just delta x. So sorry. I was going to write delta t underneath it, but whatever. We'll just do delta x first. That's fine. So you get 1.05? Okay, I can believe that. All right, let's just see what delta x is. So 20 plus 5 times 1.1 times 1.1 minus 20. Here, we'll do steps. So this first number is 26.05 minus this number on the right was 25. So yeah, you're absolutely right. It's 1.05. Yeah, you're absolutely right. That's 1.05 is our answer, right? And now if we want to find the average velocity, we just take 1.05. Yeah, you can definitely cancel out the 20 meters, that's for sure. I'm trying to go step by step. Okay, 1.05, we divide by the time interval, which is going to be 0.1 seconds, right? Or 1.1 seconds minus 1 second. So now we're going to get like 10.5 or something, right? So the average velocity now is 10.5. What we want to do now is we basically want to repeat this process where what we're going to do is we're going to change this 1.1 seconds to a 1.01 seconds, okay? So here's what I'm going to do. We're going to copy paste this. And I'll move this down a little bit too. And we'll change the color for this part so it's clear we're doing something new. This one red. So next thing we want to do is we want to make our time interval go from this to 1.01 seconds. So this is going to have to become 0.01, and this is going to have to become 1.01. So let's put those in. So we go from, we just changed this to 0.01, and right here 1.01 seconds. We do the calculation again. So now this first term right here is 25.1005. So delta x is going to be equal to, looks like 0.1005. So then to do the average velocity, we're going to get 0.1005 divided by the time interval, which is going to be 1.01 seconds, minus 1 second. So we're going to get 10.05 meters per second. That's our average velocity. Then we need to do it one more time. I'm going through this last part kind of quickly here because I'd like to take a break. So now we copy paste this one, copy paste, come down here, make it purple. We just need to change this to 1.001. Same thing here. Same thing here. I need a little more room. Okay, let's make more room to fit it in there by just scooching that to the left a little bit. Oops, grab this. So for the final time interval, we're going to 1.001 seconds. Does anyone want to make a prediction in the chat before we actually do the okay, you already calculated. I was going to ask if anyone want to make a prediction about what was going to happen. Because you can kind of see the pattern here, right? So 15 became 1, you got a 0 in between, right? 10.5. You get another 0, 10.05. So you can kind of see the pattern, right? The next one's going to be 10.005, right? Can everyone see that? 15, put a 0 in between them, put another two zeros, then 3 zeros, right? Okay, so these end up being for our final answer, I'm going to skip the step. I'll let you do it yourself if you want to. You should be able to easily prove that the average velocity here ends up being 10.005 meters per second. Now, this is kind of interesting, right? Because our goal was to find the instantaneous velocity by doing this kind of successive approximation method, where here delta t was 1 second, here delta t was 0.1 seconds, and then it was 0.01 seconds, and then down here it was 0.001 seconds. And actually what you can see is you can probably predict what the velocity is going to approach if we started to let this distance become 0, right? What's it going to get to? You're just going to keep putting 0, 0, 0, 0, eventually it's going to be 10, right? That's kind of nice, right? That's a numerical approximation, and we can show that we get you can see where it's going, right? So the final thing to do, it says, derive an expression for the cheetah's instantaneous velocity as a function of time, and then you use it to find the velocity at 1 and 2 seconds. So for this, we just need to take our equation right here, come down here to the end. So this is part D. So our goal here is to find the actual velocity as a function of time, right? And to do that, what we said was you just take the derivative of this expression, right? We know that Vx as a function of time should be equal to the derivative of x with respect to t, which is going to be equal to the derivative of this first term. What's the derivative of 20 with respect to t? And then what's the derivative of this? 5 meters per second squared t squared. What's the derivative of that going to be? 10t, right? We do need to include the units, and you might wonder, do we do anything with the units when we take derivatives? And the answer is no. You leave the units alone. So you bring the 2 down in front, 2 times 5 is 10, and then you just do times t. And if you leave the units alone, the units for your velocity should work out just fine. And now we can see that if we plug in 1, the velocity at 1 second, we get 10 times 1, which is obviously 10. It's 1 second. But the units will cancel. The second and the second cancel, and we get that this is 10 meters per second. So doing the very laborious method of just making the interval smaller and smaller and smaller, you get basically the same answer, out to whatever precision that you happen to want. The problem also asks us to find the velocity at 2 seconds. Let's do that really quickly. You take 10 times 2, and the answer is 20 meters per second. So we can see the cheetah is speeding up. And the cheetah will continue to speed up at a rate of about 10 meters per second every second. That's what this tells us. After 3 seconds, the cheetah's speed is going to be 30 meters per second, and I suspect that's about as fast as a cheetah can go, because I think cheetahs can run from between 60 and 70 miles an hour, and 30 meters per second is pretty close to 70 miles an hour. So, there we go. That's it. A little simple example to introduce the idea of taking a numerical limit combined with showing that we can take a derivative too to kind of shorten the process. Notice I said average velocity on every term. These are all average velocities, right? Because they involve doing this. And this, we put Vx. This means instantaneous velocity now, okay? As soon as the average is not written there, we mean instantaneous velocity. Sometimes the instantaneous velocity and average velocity will be the same. Could we not have skipped all of that and taken the derivative of the original function? Obviously, yeah. That's the point of part D, Hudson. But it doesn't make it any less, educational, right? This is just to show you that what we're saying here about this limit thing actually means something. And also to say, like, what I was saying up here, which is that if I really do have a curve like this, and I want to find what the velocity is, you take the slope of the tangent line, which you can also do by just making the denominator smaller and smaller. So, okay, let us take a break. It is 3:08. We'll take a break until 3:18 p.m.